average that you'll ever take. And the reason I say that is because the average you're about to figure out right now not only governs this kind of silly data set of keys, it also governs how much you pay every month for your car insurance. It also talks about why your GPA is what your GPA is. It also talks about why spam email shows up on your inbox. It's so far-reaching what we're about to figure out right now. It explains why craps is so appealing to gamblers, as you guys figured out 105 last term. What you're about to figure out, the mean of a grouped distribution, is prevalent in your lives more than you'll ever know. Until this class is over, then you'll be like, oh God, yeah. Now I know I'd be so excited to do too. So how do we do it? How do we figure out the average of this group? I'm going to clear off these scratches. Because unlike the median, we actually have to use the actual data points now. We can't just say it's the biggest or the smallest we can, so we now have to use those data points. All right, what are you thinking? Let me hear some ideas. Average. We're going to need more board for this, so I'm going to slide it over to the side. What do you think? What do you think? Ooh! Who said that? That was a wonderful idea. Tell me again. Kelsey, thank you. Area. Love that. So area in what way? So the first bar has what area? 10. It does, doesn't it? 1 times 10. What's the next bar have an area of? 40. Well, okay, good, good. I like the way you guys are calculating area right now. It actually has an area the same as the first one. But you're talking about data area, which is correct. Yes, I love that idea. Why does it work? So first of all, let's make sure everybody understands what Kelsey just said. So she said find the area of each bar. So she said 1 times 10. And then she said 4 times 10. And I'm guessing 7 times 7. And then 10 times 1. And then 13 times... Can I write this in a non-geometric fashion? Because I love the visual. It's perfect with the visual. But sometimes we won't have this. We'll have a distribution without the graph. So if we can do it in arithmetic terms, we can always apply it to anything. So I'm going to write down. I think I see what Kelsey's getting at. I'm going to put x as a data point in our new distribution. So I'm going to put x, and I'm going to call it a class mark. Because I think this is what your book calls it. When you have a distribution like this given to you in a graphical form or a distribution form, I think they call those numbers 1, 4, 7, 10. I think they call them class marks. You don't have to memorize that. I just want you to know that that's what we're going to be writing down for data. So the data is 1, 4, 7, 10, and 13. Beautiful. Beautiful, 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 beautiful. So that would be, if you will, the length of your rectangle. What's the height of your rectangle? 10. The frequencies, exactly, the frequencies. So I'm going to put that as an F for frequency over here on the... Well, it would be, except technically, I love this. Linda said, wait a minute, this doesn't look like a scatter plot, like an XY. It's actually, believe it or not, only one variable. No, I like that you're noticing it as a t-table. That's good. That's very, very good. But the idea actually is it's not a t-table in the classic sense, because this is not a variable dependent on this. It's simply an indicative of shorthand or efficiency. I'll get back to that in a second. So what's F for a class mark of 1? 10. What's F for a class mark of 4? 10. You guys are all over this. 7, 1, and 2. And Linda, I want to come back to your point about an XY table. Really, the only reason we're doing this is because I don't want to go 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. 4, 4, 4, 4, 4, 4, 4, 4, 4, 4. 7, 7, 7, 7, 7. I mean, that's going to get annoying real fast. It's more efficient to do it this way. I mean, this is why we invented multiplication. Because we ran out of fingers, we got tired of adding. So, what Kelsey, is that right? Kelsey told me to do is, she said, take the area of the rectangles. I'm going to call that x times f, just to give it an arithmetic construct that can apply across the board. So 1 times 10 is 10, 4 times 10 is 40, 49, 10, 26. Okay, so what are these numbers right here? Besides awesome. But what do they stand for, huh?
Total number of keys.
Say that again, Johnny.
Total number of keys.
So what's this 10 right here? Well, the total number, I think, if I may.
If you add all of those.
Thank you. If I add up using big sigma, add up the x times f column, I'm going to get the total number of keys in the class, yes? So let's see, that's 50, 99, 109, 140, 135? Check me on that.
135.
135, thanks, sir. Excellent. FYI, from last class, how many keys did we have? Raw data?
41.
141. Damn close, huh? Remember how we had that offness? The potential for offness within each bar? It works itself out. Because where you're going to be too high on some bars, you're going to be too low on other bars. And sometimes you'll be just right. And the idea is, some people ask, why? Why? Hold that question for a couple more minutes. Because that's a great question. Why does it work itself out? Good. Buddy's over there going, I don't buy this crap. That's good. That's good. I got a great answer for you. So what is this 10 right here?
The number of keys in that.
Good. That was perfectly said. It's the number of keys in this first group. This is the number of keys in this group. This is the number of keys in this group. Do you see how those numbers are vastly different within the overall data set? That's why you can't just go 1 plus 4 plus 7 plus 10 plus 13 and divide by 5. Which a lot of students are going to want to try to do. Oh, just add up the 5 data points and divide it by 5 and that's your average. That assumes that you've got equal frequencies across the board, which you might not have, which we definitely don't have in this case. You've got a great data set here. It's ridiculous. Cool? All right. So what do we do with this?
Divided by the total number of F.
The total number of F's, which is our frequencies, yes? So we're going to take this bad boy, sum it up. Sum of F's is going to be 30, right? That worked out nice. So our average, taking these things together, is it okay that I use these little shorthands here, friends? I like that big sigma. It comes in handy in this class very often. It's just a nice way to add things up. So we're going to add up that, which is the total number of keys. Think about units on this. That's total number of keys. That's the total number of students. And if I divide them, I get keys per, and that is the unit I want, right? That's the unit I want. That's why I want this class to not be formula-based, or to be logical-based. Some people are going to go, what do I divide? Do I divide 30 by 135 or 135 by 30? Well, think about it. If you divide 30 by 135, that's students per key. That's not what you want. You want keys per student. So, and this is one of those things I made you guys in 105 torture do that one project by dimensions. Because it's one of those things as Americans we lose very early on in math classes. The logic of a dimension. A foot versus an inch versus a mile versus time. You hated that project. I'm sorry. It's because you're an American math student. Of course you do. So, the grouped X bar version is going to be the sum of that XF over the sum of that F, which ends up being 135 over 30, which is going to be, that's almost exactly 4.5, isn't it?
It is.
Yeah. What was the exact-ish? 4.7. Hot damn! We're within 2/10 of a key of the true value. Huh? 2/10 of a key, 1/5 of a key. I call that close. I call that close. In 20 years of doing this, I've never been off by more than half a key. I call that awesome. But now, I can call it whatever I want. I can call it awesome, I can call it close, I can call it crappy. It doesn't really matter. The fact of the matter is that this estimate, keys per student, is so close to that 4.7. And the reason it's great is because if you encounter a distribution like this now, you can pull meaningful data off of it without having to have the actual raw data. You see what I'm getting at? Why is it so important? If you are given your data in this form, there is definitely some stuff missing in it. The same thing that you guys mentioned on the second day of class when I showed you the environment, the company with 20 employees, all the numbers of products they had made, and then we grouped it into a distribution. And I said, why is this better? And everybody said, oh, it's more visual, it's more organized, awesome, awesome, awesome. I said, how is it worse? And you guys, right away you said, we've lost the raw data, which means we don't know how many of this and how many of this and how many of this. We just know that there are this many of this range. And I said, don't worry. There's this beautiful thing called the law of large numbers that kicks in. And I want to show you a simulation of that momentarily. Carly, go.
So what if you have like this same whole setup, but your data on the bottom instead of like 1 to 3 or whatever is bigger?
Are you hearing this question? It's a great question. What if the data isn't broken like I've done it here by groups of 3, but it's grouped by groups of, say, 5? 0 to 4, 5 to 9, 10 to 14, or Lord, hope help us, 0 to 9, 10 to 11. Can I show you?
Yeah.
I think I can show you an answer better than tell you an answer, if that's okay. Let me pull this down. And part of the answer is it's more of an art form than a distinct answer, but hold that thought because it's a great question, like I said. What I've done right here, let me see if it can fit better. That's not bad. Pull it down a smidge. I grabbed the wrong thing. There we go. That's better. Okay. The window here doesn't fit the screen there, unfortunately, so I think we can see everything now. Okay. Now this spreadsheet will get better over time. It will get better over time, and the reason I say that is because I don't have your key data tied into it yet. I'd eventually like to build a spreadsheet that's based off of the key data that you guys put in on the first day.